In this presentation we will discuss about current trends in parallel and distributed computing. Introduction and impact on current and future technology. Parallel and distributed computing forms the backbone of modern systems by allowing multiple processors and networked machines to work together on complex tasks, improving performance, scalability, and reliability. Today, it enables technologies like cloud computing, big data analytics, artificial intelligence, and real-time services that handle massive workloads and user demand. In the future, it will be critical for exascale computing, autonomous systems, smart cities, and advanced AI, driving faster, smarter, and more energy-efficient computing. The field of parallel and distributed computing has grown significantly over the past several decades, driven by the need to solve larger and more complex problems more quickly. In the early days, parallel computing relied on specialized supercomputers that had multiple processors working on tightly connected tasks, mainly for scientific and engineering applications. As technology progressed, multi-core processors became common in personal computers and servers, enabling parallel execution of programs even on standard machines. At the same time, distributed computing emerged, connecting multiple independent computers over a network to work together on shared tasks, which led to the development of computing clusters, grids, and eventually cloud computing platforms. Today, parallel and distributed systems are widely used in areas like big data processing, machine learning, artificial intelligence, scientific simulations, and high-performance computing, handling workloads that were once impossible on a single machine. Looking ahead, heterogeneous computing is becoming increasingly important, where CPUs, GPUs, FPGAs, and specialized accelerators work together efficiently to process specific tasks within the same system. Another emerging trend is edge computing, which moves computation closer to where the data is generated, such as on IoT devices and sensors, helping to reduce latency and enable real-time decision-making. Current trends in parallel and distributed computing. Modern systems increasingly rely on cloud-native and service-oriented architectures to provide on-demand scalability using containers and serverless platforms. Performance-intensive workloads now use heterogeneous hardware, combining CPUs with GPUs, TPUs, and FPGAs. Edge and fog computing bring processing closer to data sources to reduce latency, while AI-driven techniques optimize scheduling, load balancing, and fault prediction. At the high end, exascale computing enables massive parallelism for scientific and AI workloads, and emerging quantum classical hybrid systems promise new capabilities for complex problem-solving. Cloud-native computing focuses on building applications specifically for cloud environments, making them scalable, resilient, and easy to deploy. It often uses a microservices architecture, where each service is independent, allowing faster updates and flexible scaling. Tools like Docker and Kubernetes are used to manage containers, making deployment and orchestration efficient and reliable. Service-oriented computing, or SoC, designs software as loosely coupled services that communicate over standard protocols, enabling reusability and modularity. By combining these approaches, organizations can create applications that are flexible, maintainable, and future-ready, which are widely used in modern web platforms, enterprise systems, and cloud services. Heterogeneous computing has evolved from traditional single-processor systems to systems that combine CPUs, GPUs, FPGAs, and AI accelerators for more efficient task execution. It assigns each task to the most suitable processor, improving performance and reducing processing time compared to using just one type of processor. This approach is widely used in high-performance computing, AI and machine learning workloads, graphics processing, and scientific simulations. Heterogeneous computing also optimizes energy efficiency by using edge computing brings computation and data storage closer to the data sources, such as IoT devices and sensors, reducing latency and improving real-time responses. Fog computing extends cloud capabilities to the network edge, acting as an intermediate layer between edge devices and the cloud for processing, storage, and networking. These computing models evolved due to the explosive growth of IoT and real-time applications, where sending all data to centralized cloud servers became inefficient. Edge and fog computing optimize bandwidth usage, reduce latency, and enhance reliability for applications such as autonomous vehicles, smart cities, and industrial automation. Together, they enable scalable, low-latency, and efficient distributed systems, complementing cloud computing for modern data-driven applications. AI-driven optimization uses artificial intelligence techniques to improve performance, resource allocation, and scheduling in parallel and distributed computing systems. It has evolved with the rise of big data, cloud computing, and high-performance computing, where manually managing resources became increasingly complex and inefficient. AI algorithms, including reinforcement learning, genetic algorithms, and predictive analytics, help dynamically allocate tasks to the most suitable processors or nodes. This approach reduces execution time, balances workloads, and improves energy efficiency, making systems more responsive and cost-effective. AI-driven optimization is now applied in scientific simulations, cloud services, edge computing, and heterogeneous systems, enabling smarter, faster, and more scalable parallel and distributed applications. Hybrid architectures combine classical CPUs/GPUs with emerging quantum processors for specialized workloads. Quantum processors handle complex computations like optimization, cryptography, and quantum simulations. Classical quantum task distribution. Tasks are divided. Classical systems manage control and preprocessing. Quantum systems handle high-complexity computations. Scalable future systems enables next-generation exascale computing and advanced AI workloads. Research and development focus, still emerging, but promising for breakthroughs in speed, parallelism, and problem-solving capability.